So my name is Bob Crovella, and I am officially my term is technical enablement. It's kind of a nebulous term because my job is a bit nebulous, but my purpose in life is to help Dell and make Dell be successful with GPU-enabled servers. And so what I want to talk to you today about is the GPU computing ecosystem. And it's kind of a general term, but really what I'm going to do is just give you an overview of what GPU computing is all about, why it's interesting, hopefully tell you a couple things you didn't know, and then I'll mention, if you want to come talk to me after, if you want to see some demos, I'll talk about this at the end, that you guys have a nice CUDA cluster here at MS&T already, so I can actually run some demos or show you how to log in and do some cool stuff with your CUDA cluster, which is running on Dell hardware, I'm pretty sure. I'm not mistaken. So let's get started. GPU acceleration is all about heterogeneous computing, and heterogeneous just means we're combining two different elements to get our job done. The CPU has done yeoman service for these past decades, and it turns out that we've all hit a variety of barriers, and so the CPU hasn't necessarily been delivering the computing returns that we would all like. And people started discovering that there's other ways to skin the cat. And so the GPU is also a piece of technology that's been developing over more than a decade anyway. And it has had kind of a different set of forces that are driving it. And the forces that are driving it have led to a bunch of design decisions that make a GPU look fundamentally different than a CPU, almost at any level of architecture that you're talking about. We solve problems different ways. We allocate transistor budgets different ways. We do a lot of things that are different than a CPU, but it's actually, it turns out it is a general purpose computer underneath the hood. It's just a different kind of one. And so this process of combining these two somewhat dissimilar computing elements together is something that people have really latched onto in the last 3, 4, 5 years as a way to solve bigger and bigger HPC challenges. And so we're not replacing the CPU by any means. The CPU is still doing a lot of important stuff. We're just letting the CPU do what it's particularly good at and adding the GPU to let it do what it's particularly good at. And so people are using this technology, and they're discovering that if I have a processing element in my system that has something like 10x the number of flops available to it, and it also has a corresponding increase in the amount of memory bandwidth, sure enough, I can actually get something approximating 2x, 5x, or 10x coming out the other end on my real-world codes. And so this is the attraction. It's not a science project anymore. It's not a top 500 stunt anymore. It's real science, and we've been doing real science for a long time. And most of the big codes in many spaces, molecular dynamics happens to be kind of a poster child, but all kinds of computational physics, computational chemistry, pretty much any area of computational science is using GPUs for very important major codes to get the science done. So this is really kind of an unprecedented value, because if you look at what you're doing, you're fundamentally replacing a certain amount of computing hardware with a much smaller amount of computing hardware to get the same or more work done. Stated another way, for the same budget, I can get a lot more work done. This is really what people have come to expect out of computing over the last 2 or 3 decades, right? It's Moore's Law kind of continuing. And we hit a little bit of a flattening in the rate of performance and the rate of progress of performance in computing. And so GPUs are kind of stepping into this gap and delivering the kind of 2x, 4x increases that people have been wanting out of their computing hardware. And we're doing it in a very small package with a relatively small budget, power budget, dollar budget, etc. And it's not, we're by no means at the end of this evolution. We are joined now in the past year or so by Intel, who made their formal announcement of the Xeon Phi about a year ago, a little less than a year ago. And a lot of people thought that that was going to kind of rock the boat for NVIDIA, and it's certainly a very significant development, no doubt. But it appears that there's a lot of room in this space. I'll just give you 2 data points. The first is the one you see here on the screen, is that people are doing surveys and discovering that we're not really losing any momentum, at least based on installs and delivery of systems and things like that. And the other thing is, if you listen to NVIDIA's financial results, we just announced this most recent quarter where we announced financial results. It was our biggest ever revenue quarter for our Tesla business, which is our GPU computing business. And so this is now 6 to 9 months after Intel has entered the market, and we're making more money than we ever did before on GPU computing. So there's a lot of room in this, and really what you're observing is not so much some kind of interplay between NVIDIA and Intel, but the fact that we're starting to reach a tipping point, or there's a continuous tipping of the market from ordinary CPU-centric HPC to accelerated computing, heterogeneous computing, as a way to solve the big problems. We're seeing this in a lot of different industries. We're seeing it in computer-aided engineering and physics. I've mentioned some of these already. Climate and weather is actually, I know it's on this slide, but it's probably going to take the longest to get to some of the level of technology that some of these other industries are in. But material science, computational chemistry, all of these folks are seeing dramatic speed-ups that are making their investment in GPU computing worthwhile from the standpoint of porting and code development. And if we look at it from the progress of time, we also see that there's a tremendous increase in the number of applications that have been ported to take advantage of GPUs over the past 2 years, 3 years, or even 5 years. We've been in this space for about 5 years now. This is just another look at some of these applications, and if we compare the way these applications running versus if you were only running on a CPU, we see once again we're getting these kinds of numbers, these kinds of speed ups when we apply the GPU to some of these problems. We also, another thing that you may have heard about GPUs, or maybe if your viewpoint on the GPUs was shaped by what was happening 3 to 5 years ago, you might still have this idea in your head that it's a science project or that it's a stunt or something like that. But we've now got some very, very large systems that have GPU acceleration built in, and probably the biggest one that I know of anyway is Titan at Oak Ridge, which has a very large number of GPUs in it. And some of the interesting work that's come out of the Titan project, not only is the fact that GPUs are really becoming mainstream and available to a wide variety of scientific researchers. Anyone really, as far as I know, in the scientific community can sign up and submit a project and request time on Titan. But more importantly, or at least from the standpoint of what I'm trying to explain here, we're discovering how to and how well codes scale when we talk about very, very large numbers. Taking a code and making it run on 1,000 GPUs or 2,000 GPUs or 3,000 GPUs or 5,000 GPUs and making it run well and delivering interesting returns for the utilization of the hardware. This is also happening. So this is another example of the fact that GPUs are really starting to penetrate all areas of HPC, even some of the biggest scaling problems that we know of. And not only that, but GPUs are delivering all of this with a lower cost to deliver the system, a lower cost to maintain the system, a lower cost to deliver the energy to the system. And we're in some of the top positions on the Green 500, and we're also delivering this level of computing power, relatively speaking, in a much smaller space. So if it took you 10 racks to get your problem solved 10 years ago or 5 years ago or a couple of years ago, and you switch over to GPUs, you very well may discover that you can do the same level of computing work in a single rack. And so now the question is, do you just save money, or do you actually buy 10 racks and tackle bigger problems? So I'm going to switch gears a little bit. That's kind of the marketing stuff. And what I want to talk about, uh-oh, something just happened. Let me see if I can fix this. I guess we don't have our IT guy in the room. I hit the wrong button, obviously. Sorry about that. So what I want to do now is just give you an overview. Since this is kind of a research and technology day, I don't want to sit here and just talk the entire 25 minutes about what's cool about GPUs and try and sell you on them. What I'd really rather have you do is learn how to use them. And I'm not going to be able to do that in the space of the next 5 or 10 minutes, but I want to give you a little bit of a picture that it's relatively easy. And you may have also heard about GPUs that they're hard. And I'm not here to tell you that parallel programming isn't hard, or that taking advantage of an accelerator is anything like recompile and run, if you've ever heard that. I think people are generally discovering that's not really true. It's going to take some effort, but there's a number of different ways to skin the cat, and some of those ways are relatively painless, relatively low barrier to entry, and that's really what I want to try and expose to you here. So if you want to take advantage of GPU computing, if you go back to the very first slide I showed, it was a heterogeneous computing thing. We've got two computing elements. The fundamental strategy is we want to take a small portion of our code that's doing the heavy lifting, so to speak, where a lot of the work is getting done. We want to focus on that, we want to accelerate that, and we want to leave the rest of it alone, basically. Everything that's handling I/O or handling user interaction or scheduling of work, things of that nature, typically we're going to leave those alone, and we're going to focus on a relatively small portion of the code that's doing the heavy computational work. And that's really what we're going to accelerate. And in so doing, that's how we intend to get our speed up. And as we look at different approaches to accelerate applications, we discover that they're all going to do that under the hood. Some of them are going to do it in a very explicit way where you're exposed to the programming language and you're seeing this partition of work at the source code level. And then we can go all the way to the other end of the spectrum where you have no knowledge really of what's going on under the hood at all, except things run faster. And I'll just give you one real brief example of that, is in applications. One of the applications that you might have heard of or used is MATLAB. And so if you're using MATLAB, you can take advantage of GPUs in several different ways. But MATLAB treats a GPU as a first-class citizen, so it has explicit control of the GPU built into MATLAB. And if you want to do matrix operations or linear algebra or Fourier transforms or something like that on large data sets in MATLAB, you can do that on the GPU just by specifying an array as a GPU array instead of a regular MATLAB array. And from then on, all of the work happens on the GPU. It's that level of intensity in terms of what you have to learn. So it's not a very high barrier to entry if you're used to MATLAB and you want to make your MATLAB code run faster. But there's a whole range of applications, literally over 200 applications that are relevant to a significant number of people, not just an application that someone wrote for their own work, but generally speaking, many of these are open source applications that are well known in the scientific community. I mentioned a few of them already, like AMBER. There's a lot of them in the molecular dynamics space, the physics space. If you're using one of those codes already, you shouldn't really have to do any work at all. At that point, what you really want to do is just get the GPU-enabled version of it, build it on your cluster, and then run it. So there's no real GPU coding work that you should have to do at all. And if you're using a code like AMBER or NAMDU, it is basically how that works. You're simply configuring and building AMBER with a set of switches that says use the GPU or build the GPU-enabled version. And from then on, all of your involvement with AMBER is no different than what you did before. You set up your job files the same way. The data output happens in the same way. It just happens more quickly. But there's lots of other applications. And so one of the things that you would want to do is, if you're using an application that, let's say, you didn't write, or you know that a large community uses that application, then you should definitely check to see if it's GPU enabled. You can just do that with Google. Google will give you very sensible and reliable results, but we do have application catalogs that are available that list all the applications and give you some idea of what kinds of speed ups or under what circumstances you're going to get an attractive speed up. But let's say, and so there's a lot of applications in this space. They're not limited to one area. We even have commercial applications like Adobe Creative Suite uses GPUs, and there's a lot of different spaces. In fact, one of the things that's interesting about GPU computing, because we've been at this for a while, is you can Google practically any topic you want. And so if you're interested in Hadoop, for example, a Hadoop cluster, you can find people who have taken Hadoop clusters and made them GPU aware so that they can do part of the MapReduce problem on the GPU. But anyway, there's lots of different applications that are GPU accelerated. They come in a lot of different spaces. So if you're using an application that a lot of other people are using, it's definitely something to look into. But let's say you're not. Let's say you wrote the code or you've checked and it's not accelerated. Then what are your options? Well, if you're using a library, let's say, if you've already taken advantage of something like FFTW as a library to accelerate or to run your Fourier transforms, it's a relatively straightforward process to take some kind of scientific library like FFTW or a BLAS library and then convert that so that that portion of your code runs on the GPU. And many people do this and they get interesting speed ups by doing it. There's lots of libraries that I could talk about here. Roughly speaking, about a third to a half of these libraries originated from NVIDIA development and research, and roughly speaking, about half of them come from elsewhere. So you're going to find that the GPU computing ecosystem is not all an NVIDIA-driven ecosystem. There's lots of people who are in this space to make money, or for one reason or another, and you'll discover that a lot of portions of the ecosystem are not really originating from NVIDIA. But if you have interest in any of these areas, you can find libraries that'll do it. And for example, ArrayFire, I think, is on here. ArrayFire is another sort of mini computing language, something like MATLAB. It's not really like MATLAB, but it's a language unto itself. And so if you're interested in mathematical operations, that might be something you can check into, and they do a great job of utilizing GPUs. Let's say that you're not doing that. You've written all this code, you're not taking advantage of any libraries, and your code doesn't have obvious scientific library type operations like FFT or linear algebra or something along those lines, sparse matrix operations. You don't have any of that in your code. But you'd still think that you're doing a lot of heavy lifting in your code. Maybe you even know that there's some areas where that's kind of focused in your code, and you would like to see if the GPU can help you out there. Well, the next level of complexity that you could drill into is something called directives. And directives allow you to basically sprinkle pragmas or comments, or it's available in Fortran, so there's an equivalent directive construct in Fortran. But basically, we are now putting the burden on the compiler to do all of the GPU code generation, all of the structuring of your code to generate GPU kernels. Work that gets done on the GPU, and you're doing a relatively simple annotation of your code. So you're not actually changing your source code, or you don't have to change your source code to take advantage of directives. This does require a specific compiler, so that you're not going to get this with GCC, for example, but you can get a compiler. Portland Group has compilers that will do this, and there are some other compilers out there that will do this, and they will basically allow you to drop a relatively simple construct into your code and then let the GPU do its magic, or let the compiler do its magic to enable the code on the GPU. This is obviously not the most precise way of taking your code and making it usable on the GPU, but it's a relatively low barrier to entry. It's something where you generally don't have to learn that much about GPU computing. You simply are using this directive construct to get the work done. So people do that and they get interesting results, and then if you're sufficiently motivated, you might actually want to tackle it at the language level, at the programming level. And if you want to do that, you can learn how to program in CUDA C, CUDA C++, Fortran. We actually support Python. We support other languages, so you can program in Java for a GPU if you wanted to program in Java, for example. There's a number of languages. Again, not all of them originate from NVIDIA. If you like to use R, the statistical language, you can use R on GPUs. Not all of these languages originate from NVIDIA, as I said, but nevertheless, these allow you to have the most precise control over the coding that you do. And if you look at CUDA C or C++, for example, which is what I'm showing here, you'll see that, yes, CUDA C has some boilerplate associated with it, and it has some additional syntax associated with it. But the intent of your code actually generally is visible and preserved as you go from your standard C implementation to a CUDA C implementation. That's why we call it CUDA C or CUDA C++, because it's fundamentally the C or C++ language with a few extra pieces of syntax thrown in that allow you to target work to be done on the GPU. So I'm just about at the end of my presentation, and I want to mention that today we're shipping products based on our Kepler generation, which is our latest generation of GPUs. These are the products that I'm showing here are the Kepler GPUs that are for Tesla GPU computing. K20X, K20, and K10, they're targeted at slightly different spaces. K20X is kind of the high-performance flagship. It's got the highest double precision compute numbers. K20 is sort of one level down from that. It's sort of the value leader, if you will, on double precision computing performance. And then we also have a new product called K10, which is new for the Kepler generation, that allows you to do relatively high-performance single precision code, but it's not very fast at double precision. Anyway, these are just speeds and feeds. I just wanted to let you know this is kind of our current generation of product. And I think I may have a roadmap slide here. I do. And what I want to mention here is that we've been at this space for about, roughly speaking, 5 or 6 years now. And a lot of people ask us, well, what are the returns in the HPC space? How can you justify it? Will NVIDIA go away? Are you guys just going to give up? The answer is no. But the reason is that this roadmap here, which looks pretty impressive if you talk about the progress of compute performance, because it's roughly doubling or more in each generation, this roadmap is actually not dictated by our compute products. This roadmap is actually dictated, and has been for a long time, dictated by the graphics space, which is also a highly parallel computing space underneath. When you peel back the graphics APIs, especially the APIs today, what they imply and require out of the graphics processor is something that can handle arbitrary graphics code. In other words, they require a general purpose compute engine underneath the hood, which has all of the things that you'd expect out of a high-level language, like branching and control flow and handling various data types and things of that nature. That's the reason that we have a roadmap like this, and when we create our Tesla GPU computing products, like the ones that I just showed you for the Kepler family, we do that basically by taking the GPUs that we were going to develop anyway and creating the GPU computing product based on that. But with or without GPU computing, which today is still a relatively small percentage of our total revenue, with or without GPU computing, we have a roadmap of GPUs that we're going to be developing for all of the spaces, including graphics, that we service with those GPUs. So this is not going away. This will continue. If you want to get started, there's a lot of resources out there. Again, I would just say Google it, but it's not, pretty quickly if you Google GPU computing, you'll find hits on various NVIDIA websites. I will be available after this for at least till 1 o'clock, let's say, and I'm in the St. Pat area where all of the vendors are. I'm in the Dell booth, and if you'd like to see any kind of quick